To ring signatures. Welcome to the channel. Please consider subscribing. I produce videos daily, covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we're exploring one of the most fascinating cryptographic primitives in modern privacy technology: ring signatures. Ring signatures represent a breakthrough in how we think about digital signatures and anonymity. Unlike traditional digital signatures where the signer's identity is explicitly revealed, ring signatures allow a member of a group to sign a message on behalf of the group without revealing which specific member created the signature. This creates a powerful form of signer ambiguity that has become foundational to privacy-preserving cryptocurrencies and anonymous authentication systems. The concept was first introduced by Ron Rivest, Adi Shamir, and Yael Talman in 2001, and the name ring signature comes from the ring-like structure of the verification algorithm. The key innovation is that any member of a group can create a signature using their own private key and the public keys of other group members, without needing any cooperation, setup ceremony, or permission from those other members. This is fundamentally different from group signatures or threshold signatures, which require interaction between parties. Ring signatures provide unconditional anonymity, meaning that even with unlimited computational power, an observer cannot determine which member of the ring actually created the signature. This is because the verification process treats all ring members symmetrically. There is no mathematical way to distinguish the real signer from the decoys. This property makes ring signatures particularly valuable for whistleblowing, anonymous voting, and privacy-focused cryptocurrencies like Monero. Core properties of ring signatures. Ring signatures must satisfy three fundamental cryptographic properties to be considered secure and useful. Understanding these properties is essential because they define what ring signatures can and cannot do, and they guide how we implement and verify them in practice. The first property is correctness, which means that any valid ring signature created by a legitimate ring member will always verify successfully when checked against the ring's public keys. This seems obvious, but it's crucial that the verification algorithm accepts all honestly generated signatures. If a legitimate signature could fail verification, the system would be unreliable and unusable in practice. The second property is unforgeability, also called existential unforgeability under chosen message attack. This means that someone who is not a member of the ring cannot create a valid ring signature for that ring, even if they can observe many valid signatures and even if they can trick ring members into signing messages of the attacker's choice. The security proof for this property typically relies on the hardness of the discrete logarithm problem or the difficulty of breaking the underlying signature scheme used for each ring member. The third and most distinctive property is anonymity, or signer ambiguity. This means that given a valid ring signature, it is computationally infeasible to determine which ring member actually created it. You will only know that it was one of the members in the ring. Even the other ring members cannot tell who signed it. And even if all ring members except one reveal their private keys, that final member's signatures still remain anonymous. This is sometimes called unconditional anonymity because it holds true even against computationally unbounded adversaries. There is also an optional fourth property called linkability, which some ring signature schemes include. In a linkable ring signature scheme, it is possible to detect if two signatures were created by the same ring member without revealing who that member is. This is useful for preventing double spending in cryptocurrencies while maintaining anonymity. Ring signature architecture. The architecture of a ring signature scheme consists of several components working together to achieve anonymous signatures. Let's walk through each component to understand how the complete system operates. First, we have the key generation phase. Each potential ring member generates their own public-private key pair independently, using whatever signature scheme they prefer. This could be RSA, ECDSA, EDDSA, or any other signature algorithm. The beautiful thing about ring signatures is that members don't need to coordinate or even know about each other during key generation. Each person just creates their key pair normally, publishes their public key, and that's it. There's no special ring setup ceremony required. Next, we have the ring formation process. When someone wants to create a ring signature, they choose a set of public keys to form the ring. This set must include their own public key, but they can add any other public keys they want without asking permission from those key owners. Typically, a signer chooses public keys of people or entities that make sense as a group, for example, all employees of a company, all members of a committee, or all participants in a blockchain. The size of the ring directly impacts the anonymity set. A larger ring provides stronger anonymity but results in larger signatures. The signing process is where the magic happens. The signer uses a special algorithm that combines their own private key with the public keys of all other ring members to produce a signature. The algorithm uses a technique called ring closure, where the signer creates random values for all other ring members and then solves for their own value in a way that balances the entire ring equation. This process creates a signature that could have been produced by any member of the ring. Finally, the verification process takes the message, the signature, and the ring of public keys, and checks whether the signature is valid for that ring. The verification algorithm does not identify the individual who signed. Instead, it only confirms that someone within the ring signed the message. The verification treats all ring members symmetrically, which is why the signer's identity remains hidden. Mathematical foundation. Ring signatures rely on clever mathematical constructions that create signer ambiguity while maintaining verifiability. Let's examine the mathematical foundations that make ring signatures possible, focusing on the most common construction based on discrete logarithm problems. The core mathematical structure is built on cyclic groups, typically elliptic curve groups in modern implementations. Each ring member has a public key that's a point on an elliptic curve, and their private key is a scalar value. The relationship between private key x and public key p is p equals x times the generator point g. This is the standard elliptic curve discrete logarithm relationship, and its hardness ensures that knowing p doesn't help you find x. The ring signature construction uses what is called a ring equation, or a linkable spontaneous anonymous group signature structure. For a ring with n members, each having public keys p sub 1, p sub 2, through p sub n, the signer generates random values for all positions except their own. The signer then solves for their position to close the ring. The equation typically looks like a hash chain where each element depends on the previous one, which forms a ring structure. Specifically, the signer at position S starts by choosing random values for all other positions. Let's call them R1, R2 through Rn, excluding position S. Then, for each position I, again excluding position S, they compute a challenge value using a hash function. This value, Ci, equals the hash of the message, the public key, and the previous response. This process creates a chain of dependencies. When this chain eventually circles back to position S, the signer solves for their own response value, Rs, using their private key, Xs, ensuring that the ring equation closes. The verification process checks that the ring equation holds by recomputing all the challenge values and verifying that the chain closes properly. The key insight is that during verification, you cannot tell which position was actually computed using the private key, versus which positions used randomly chosen values. They all look equally valid, which is what provides the anonymity property. The unforgeability comes from the fact that to forge a signature without knowing any private key, you would need to create a valid ring closure, but this requires either breaking the discrete logarithm problem or finding a collision in the hash function. Both are assumed to be computationally infeasible. The anonymity comes from the fact that all positions in the ring look statistically identical. There is no way to distinguish the real signer's position from the decoy positions. Verification algorithm deep dive. The verification algorithm for ring signatures confirms that a signature is valid without learning who created it. Let's walk through the verification process step by step to understand exactly what's being checked and why each step matters. The verifier receives four things as input: the message that was signed, the ring signature itself, the ring of public keys, and sometimes an additional tag for linkable ring signatures. The signature typically consists of a list of scalar values, one per ring member, and an initial challenge value or starting point for the ring equation. The first step in verification is to reconstruct the ring equation starting from the initial challenge. For each position in the ring, the verifier computes what that position contributes to the ring structure. This involves elliptic curve point operations using the public key at that position and the scalar value from the signature. Specifically, for position I with public key PI and signature component RI, the verifier computes points like Ri times G plus Ci times Pi, where G is the generator point and Ci is the challenge for that position. The next step is to compute the chain of challenges that links all ring positions together. Starting with the initial challenge value from the signature, the verifier hashes together the message, the current position's public key, and the point computed in the previous step. This produces the challenge for the next position. This process continues around the entire ring, with each position's challenge depending on the previous position's computation. The critical verification check occurs when the challenge chain returns full circle to its starting position. The verifier then checks if the final computed challenge matches the initial challenge provided in the signature. If they match, the signature is considered valid. If they do not match, the signature is rejected. This ring closure property is what enables the signature to function. Only someone who knew a private key for one of the positions could have constructed values that allow the ring to close correctly. An important aspect of verification is that it treats all ring positions symmetrically. The algorithm performs the same operations at each position, using that position's public key and signature component. There is no indication in the algorithm about which position might be the real signer. This symmetry is crucial for maintaining anonymity. Even examining the verification process reveals nothing about who signed. Anonymity guarantees. The anonymity provided by ring signatures is one of their most important and subtle properties. Let's explore what anonymity means in this context, what guarantees we have, and what the limitations are. Ring signatures provide what's called unconditional anonymity or information-theoretic anonymity with respect to signer identification. This means that even an adversary with unlimited computational power cannot determine which ring member created a specific signature, beyond knowing it was one of the ring members. This is a much stronger guarantee than computational anonymity, where we only assume the adversary has bounded computational resources. The reason for this strong anonymity is that all ring positions are statistically indistinguishable in the signature. When the real signer creates the signature, they generate random values for all other positions and solve for their own position. But to an observer, there is no way to tell which position was solved for versus which positions had random values. The distribution of all signature components looks identical regardless of which position is the real signer. This is similar to a one-time pad in symmetric encryption. The perfect secrecy does not rely on computational assumptions. The anonymity set size equals the number of members in the ring. If you have 10 public keys in your ring, then your anonymity set is 10, meaning the real signer is hidden among 10 possible candidates. Larger rings provide stronger anonymity but result in larger signatures and slower verification. In practice, ring sizes in Monero typically range from 11 to 16 members, balancing anonymity with efficiency. However, there are important limitations to consider. First, the anonymity only applies to signatures created with that specific ring. If you use the same ring repeatedly, metadata analysis might reveal patterns. Second, the anonymity set is limited to the ring members. If an attacker can eliminate some ring members as possibilities through external information, the anonymity set shrinks. Third, if an attacker controls all but one member of the ring and can prove they did not sign, they can deduce who did sign by elimination. There's also the issue of ring member selection. If a signer consistently chooses rings with particular characteristics, this might create a fingerprint. For example, if Alice always creates rings containing her 5 friends, an observer might notice this pattern. This is why cryptocurrencies like Monero use algorithmic ring selection rather than user choice. Linkable ring signatures. Linkable ring signatures extend the basic ring signature concept with an additional property: the ability to tell if 2 signatures were created by the same person, without revealing who that person is. This seemingly contradictory capability is crucial for preventing double spending in cryptocurrencies while maintaining privacy. The key innovation in linkable ring signatures is the addition of a key image or tag to each signature. This tag is derived from the signer's private key in a way that is unique to that private key, but does not reveal its actual value. Mathematically, the key image I is typically computed as I equals x sub s times h sub p of p sub s, where x sub s is the signer's private key, p sub s is their public key, and h sub p is a hash function that maps to points on the elliptic curve. This construction ensures that the same private key always produces the same key image, regardless of which ring is used. When verifying a linkable ring signature, the verifier checks not only that the ring equation closes properly but also that the key image was correctly computed by someone in the ring. This is done by verifying that the same scalar value that closes the ring equation also correctly relates the key image to one of the public keys in the ring. The clever part is that the verification process does not reveal which public key the key image corresponds to. It only confirms that the key image is consistent with some member of the ring. The linkability property works like this: if 2 signatures have the same key image, they were definitely created by the same person. If 2 signatures have different key images, they were either created by different people or by the same person using different private keys. This allows systems to detect double signing without compromising anonymity. For example, in Monero, each transaction input includes a linkable ring signature, and the blockchain tracks all key images to prevent the same output from being spent twice. It's crucial to understand that linkability doesn't break anonymity. Even though you can tell that 2 signatures came from the same person, you still don't know who that person is from the set of ring members. The anonymity set remains unchanged. You just gain the additional information that whoever signed message A also signed message B. This is perfect for preventing double spending while maintaining privacy. Verification implementation details. Implementing ring signature verification correctly requires attention to numerous details. Let's walk through the practical considerations and implementation challenges that arise when building a ring signature verifier. The first implementation concern is elliptic curve operations. Ring signature verification requires many scalar multiplications and point additions on an elliptic curve. For a ring of size n, verification typically requires around 2n scalar multiplications. These operations must be performed using a well-tested elliptic curve library with constant time implementations to prevent timing side channels. Most implementations use curve beginning with 2-5 ending with 1-9 or the ED beginning with 2-5 ending with 1-9 signature curve because they offer both security and performance advantages. Hash function selection is another critical decision. The ring signature scheme requires hashing to generate challenges at each ring position. The hash function must output values in the correct range for the elliptic curve scalar field, and it must be cryptographically secure. Most implementations use SHA 512 and then reduce modulo the curve order, or they use a hash to scalar function specifically designed for the curve. The hash must include the message, relevant public keys, and intermediate computation results to bind everything together. Signature format and encoding require careful specification. A ring signature consists of multiple scalar values, one per ring member, plus the initial challenge or key image. These must be encoded in a standardized format, typically using fixed-length byte arrays for each scalar. The encoding must be canonical to prevent signature malleability, which is where an attacker could modify a valid signature to create a different valid signature for the same message and ring. This canonicality is usually enforced by requiring scalars to be in a specific range or by using a specific byte representation. Input validation is absolutely essential for security. Before beginning verification, the implementation must check that all public keys in the ring are valid points on the curve, that all signature components are in the valid scalar range, and that there are no duplicate public keys in the ring. Failing to validate inputs properly can lead to signature forgery or crashes. Each public key must be checked to ensure it is not the identity point and that it satisfies the curve equation. Signature scalars must be less than the curve order. Performance optimization is important because verification involves many expensive cryptographic operations. Techniques include batch verification, where multiple signatures are verified together, precomputation of common curve points, and using optimized formulas for specific curve operations. Some implementations also cache intermediate results if the same ring is used repeatedly. However, optimizations must never compromise security. For example, early abort on verification failure could create timing side channels. Security analysis. Understanding the security of ring signatures requires analyzing both the cryptographic assumptions and potential attack vectors. Let's examine what makes ring signatures secure and what could go wrong. The foundational security assumption is the hardness of the discrete logarithm problem on the chosen elliptic curve. Ring signature unforgeability reduces to this assumption. If someone could forge a ring signature without knowing any private key, they could use that capability to compute discrete logarithms. Specifically, the security proof shows that a ring signature forger can be converted into a discrete logarithm solver through a technique called reduction. This means that as long as discrete logarithms are hard, ring signatures are unforgeable. The hash function security is equally critical. Ring signatures use hash functions in the challenge generation process, and these must be collision-resistant and behave like random oracles in the security proof. If an attacker could find hash collisions, they might be able to construct forgeries by carefully selecting inputs that hash to desired values. Similarly, if the hash function does not behave randomly enough, the challenge values might become predictable, potentially breaking unforgeability or anonymity. One subtle attack vector involves malicious key generation. If a ring member generates their key pair maliciously, choosing values that have a special mathematical relationship to other ring members' keys, they might be able to break anonymity or forge signatures. This is prevented by requiring that all public keys are properly validated before being accepted into a ring. Each public key must be proven to correspond to a private key that the key owner actually knows, typically through a proof of possession protocol. Anonymity can be compromised through various metadata channels even if the cryptography is perfect. For example, if a signer always includes the same set of public keys in their rings, this creates a behavioral fingerprint. Similarly, if the timing of signature creation correlates with known activities of a particular ring member, this might reduce anonymity. These are often called off-chain attacks because they do not break the cryptographic anonymity but rather use external information to narrow down possibilities. There's also the risk of quantum computers. Ring signatures based on discrete logarithm problems would be completely broken by a large quantum computer running Shor's algorithm. This means that any ring signatures created today could potentially be de-anonymized in the future if quantum computers become practical. This is a concern for applications requiring long-term anonymity. Post-quantum ring signature schemes based on lattices or hash functions are being developed to address this threat. Monero's ring signature implementation. Monero is the most prominent real-world application of ring signatures, using them to hide the true source of every transaction. Let us examine how Monero implements ring signatures and what modifications they have made to the basic scheme. Monero uses a specific type of ring signature called MLSAG, which stands for Multi-Layer Linkable Spontaneous Anonymous Group Signature. This is an extension of basic linkable ring signatures that allows signing multiple inputs together with a single signature. In a typical Monero transaction, you might be spending 2 or 3 outputs as inputs, and MLSAG allows you to create a single ring signature that covers all inputs simultaneously while producing one key image per input to prevent double spending. The ring selection process in Monero is crucial for maintaining anonymity. When you create a transaction spending an output, Monero automatically selects additional outputs from the blockchain to include in your ring as decoys. The selection algorithm uses a gamma distribution that biases toward recent outputs, because spending patterns show that real users tend to spend recent outputs more often than old ones. This statistical matching helps prevent timing analysis attacks, where an observer might guess that the real input is the newest one in the ring. The ring size in Monero has evolved over time. Initially, Monero allowed users to choose variable ring sizes, but this approach created opportunities for fingerprinting. Subsequently, a minimum ring size was enforced, and it was gradually increased from 5 to 7 to 11. As of the most recent network upgrade, Monero uses a fixed ring size of 16 for all transactions. This uniformity is crucial because it prevents users from revealing information about their preferences or from creating patterns through their ring size selection. Monero also implements several optimizations to make ring signature verification efficient enough for blockchain consensus. Each block can contain hundreds of transactions, each with multiple ring signatures, and all nodes must verify all signatures when validating blocks. Monero uses batch verification techniques that allow verifying multiple ring signatures simultaneously with significant computational savings. The verification algorithm is also designed to be memory hard to some degree, which helps prevent ASIC-based verification acceleration that could centralize the network. One challenge Monero faces is blockchain size growth. Each transaction includes a ring signature with 16 public keys, plus cryptographic proof components. This makes transactions much larger than those in transparent blockchains. Monero transactions are typically around 1.5 kilobytes, compared to 250 bytes for a simple Bitcoin transaction. This means the Monero blockchain grows faster and requires more storage. Recent research into more efficient ring signature constructions aims to reduce this overhead, while maintaining or improving anonymity guarantees. Advanced verification techniques. As ring signature schemes have matured, several advanced verification techniques have been developed to improve efficiency, security, and functionality. Let's explore these sophisticated verification methods that go beyond the basic ring equation checking. Batch verification is one of the most important optimizations for systems that need to verify many ring signatures simultaneously, such as blockchain nodes processing blocks of transactions. The key insight behind batch verification is that you can verify multiple signatures together more efficiently than verifying them one at a time. This works by exploiting the linearity properties of elliptic curve operations. Instead of advanced verification techniques. As ring signature schemes have matured, several advanced verification techniques have been developed to improve efficiency, security, and functionality. Let's explore these sophisticated verification methods that go beyond the basic ring equation checking. Batch verification is one of the most important optimizations for systems that need to verify many ring signatures simultaneously, such as blockchain nodes processing blocks of transactions. The key insight behind batch verification is that you can verify multiple signatures together more efficiently than verifying them one at a time. This works by exploiting the linearity properties of elliptic curve operations. Instead of computing separate scalar multiplications for each signature, you can combine them into a smaller number of operations. The batch verification algorithm works by taking multiple ring signatures and combining them with random coefficients. For each signature, you multiply all the elliptic curve points by a random scalar, then sum these weighted points together. If all the signatures are valid, the combined equation will hold. If even one signature is invalid, the combined equation will fail with overwhelming probability. The security comes from the random coefficients, making it computationally infeasible for an attacker to craft multiple signatures that verify in batch but where some are individually invalid. Parallel verification is another technique particularly useful for multi-core processors. Since each position in a ring signature can be verified independently, you can distribute the verification work across multiple CPU cores. For a ring of size 16, you could theoretically use 16 cores to verify all positions simultaneously, then combine the results. In practice, you need to balance the overhead of thread synchronization against the benefit of parallelization, but for large rings or many signatures, this can provide significant speedups. Incremental verification is useful in scenarios where ring signatures are verified multiple times with slight modifications. For example, if you are verifying a transaction that spends multiple inputs, each with its own ring signature, you might be able to cache intermediate results from one signature and reuse them when verifying the next. This is particularly effective when signatures share ring members, which is common in cryptocurrency applications where popular outputs appear in many rings. Ring confidential transactions. Ring confidential transactions, often abbreviated as ring CT, represent a major evolution in ring signature technology. Ring CT combines ring signatures with cryptographic commitments to hide not just the sender, but also the transaction amounts. This provides a much stronger level of privacy than ring signatures alone. The fundamental challenge that ring CT solves is this: if transaction amounts are visible, then even with ring signatures hiding the sender, an observer might be able to trace transactions by following the amounts. If you see a ring signature spending one of 10 possible outputs, but only one of those outputs has exactly the right amount to match the transaction output, then you've effectively de-anonymized the transaction despite the ring signature. Ring CT prevents this by hiding the amounts. Ring CT uses Peterson commitments to hide amounts while still allowing verification that the transaction is balanced. A Peterson commitment to an amount V looks like C equals V times H plus R times G, where H and G are elliptic curve generator points, and R is a random blinding factor. The commitment C is published, but V and R remain secret. The beautiful property of Peterson commitments is that they're additively homomorphic. If you add two commitments, you get a commitment to the sum of the amounts. To prove that a transaction is balanced without revealing amounts, Ring CT uses range proofs. A range knowledge proof is a zero knowledge proof that a committed value lies within a certain range, typically 0 to 2 to the power of 64-1 for cryptocurrency amounts. This prevents negative amounts that could be used to create money out of thin air. The range proofs used in Ring CT are called bullet proofs, which are much more compact than earlier range proof constructions. The verification of a Ring CT transaction involves multiple steps. First, verify the ring signature that proves the transaction inputs are being spent by their owner. Second, verify that the sum of input commitments equals the sum of output commitments plus the fee, which proves the transaction is balanced. Third, verify the range proofs for all outputs to ensure no negative values. All of this happens without the verifier learning any of the actual amounts involved. This combination of ring signatures and confidential transactions provides both sender anonymity and amount privacy. Triptych and Arcturus ring signatures. Triptych and Arcturus represent the next generation of ring signature constructions, offering significant improvements in signature size and verification time compared to earlier schemes like MLSAG. These advanced schemes are important because they help address the blockchain bloat problem while maintaining or improving privacy guarantees. Triptych, introduced in 2020, uses a different mathematical approach based on arithmetic circuits and zero-knowledge proofs. Instead of constructing a ring equation that chains through all members, Triptych proves knowledge of a secret key corresponding to one of the public keys in the ring using a logarithmic size proof. For a ring of size n, Triptych signatures grow only logarithmically with n, rather than linearly as in MLSAG. This means doubling the ring size adds only a constant amount to the signature size, rather than doubling it. The key innovation in Triptych is to represent the ring membership proof as a constraint satisfaction problem. The public keys in the ring are arranged in a matrix, and the signer proves that they know a secret key for one position in this matrix without revealing which one. This is accomplished using polynomial commitments and evaluation proofs. The verifier checks that the prover's committed polynomial evaluates correctly at specific points. This indirectly proves ring membership. Arcturus builds on Triptych by adding support for confidential transactions more efficiently. While Triptych can be combined with ring CT, Arcturus integrates amount commitments directly into the ring signature structure. This results in smaller combined signatures than using Triptych and bulletproofs separately. Arcturus achieves this by using a single zero-knowledge proof system that proves both the ring membership and the range properties of committed amounts simultaneously. The verification algorithm for Triptych and Arcturus is more complex than MLSAG but offers better asymptotic performance. For very large rings, which are desirable for stronger anonymity, these schemes become significantly more efficient. The trade-off is that they require more sophisticated mathematics and are harder to implement correctly. They also require a trusted setup or transparent setup depending on the specific instantiation, which is a different trust model than MLSAG, which requires no setup at all. Verification performance analysis. Understanding the performance characteristics of ring signature verification is crucial for deploying these systems in real-world applications. Let us analyze the computational costs, scalability properties, and optimization strategies for ring signature verification. The dominant cost in ring signature verification is elliptic curve scalar multiplication. For MLSAG with a ring size of n, verification requires approximately 2 times n scalar multiplications plus n hash function evaluations. Each scalar multiplication involves around 256 elliptic curve point doublings and point additions for a 256-bit curve. On a modern CPU, a single scalar multiplication takes roughly 50 to 100 microseconds, so verifying a ring signature with 16 members takes about 1.6 to 3.2 milliseconds. This might seem fast, but it becomes a bottleneck when verifying entire blocks. A Monero block might contain several hundred transactions, each with multiple ring signatures. Verifying a full block could take several seconds. This is significant when you need to validate the entire blockchain, or stay synchronized with new blocks arriving every 2 minutes. This is why batch verification and parallel processing are so important for cryptocurrency nodes. Memory usage is another consideration. Each ring signature contains n public keys, which must be looked up from the blockchain database. For 16-member rings, this means 16 key lookups per signature. Database access patterns and caching strategies significantly impact verification performance. If the same outputs appear in many rings, which is common, a good caching strategy can dramatically reduce database lookups. Verification time also depends on the ring signature scheme. MLSAG has linear verification time in the ring size. Triptych has verification time that grows as O of n log n for n ring members due to the polynomial evaluation checks. For small rings like size 16, MLSAG is actually faster, but for larger rings like size 128 or 256, Triptych becomes more efficient. This creates an interesting trade-off between ring size, anonymity, and performance. Network bandwidth and storage are impacted by ring signature size. Larger signatures mean larger transactions, which increases blockchain size and network traffic. MLSAG signatures are about 32 n bytes for n ring members, so a size 16 ring is about 512 bytes. Combined with other transaction components, Monero transactions are typically 1.5 to 2 kilobytes. This is 6 to 8 times larger than a typical Bitcoin transaction, directly impacting blockchain growth rate and initial sync time for new nodes. Cross-chain ring signatures. Cross-chain ring signatures represent an emerging application area where ring signatures are used to enable privacy-preserving interoperability between different blockchains. This is a challenging problem because different chains have different cryptographic systems, consensus rules, and trust models. The basic idea behind cross-chain ring signatures is this: you create a signature proving you control funds on one blockchain. This signature does not reveal which specific output you control. Then, you use this proof to unlock or create funds on a different blockchain. This process is more complex than standard ring signatures because the verification has to occur on a different blockchain, which may have unique cryptographic primitives and a distinct security model. One approach uses threshold signatures combined with ring signatures. A group of validators on the destination chain collectively maintain a multi-sig wallet on the source chain. When someone wants to transfer funds, they create a ring signature on the source chain, proving that the funds have been burned or locked. The validators then verify this proof and collectively sign a transaction on the destination chain to release the funds. The ring signature ensures the source remains private, while the threshold signature ensures decentralized control of the destination chain funds. Another approach uses zero-knowledge proofs to verify ring signatures across chains. The source chain uses ring signatures for privacy, and when someone wants to prove they made a transaction on the source chain, they create an SNARK or STARK proof that verifies the ring signature. This proof can be checked on the destination chain even if that chain does not natively support the ring signature scheme. The zero-knowledge proof essentially says, "I know a valid ring signature for this transaction," without revealing the signature itself or which ring member signed. The challenge with cross-chain ring signatures is maintaining security when the chains have different security levels. If the destination chain is less secure than the source chain, an attacker might manipulate it to falsely claim that funds were transferred. Conversely, if the source chain is compromised, fake proofs could be created to steal funds on the destination chain. Therefore, careful protocol design, including appropriate timeout periods, challenge mechanisms, and economic security bonds, is necessary to make cross-chain ring signatures secure in practice. Regulatory and compliance considerations. Ring signatures and the anonymity they provide create unique challenges for regulatory compliance and law enforcement. Understanding these considerations is important for both deploying ring signature systems and participating in policy discussions about privacy technologies. The fundamental tension is between financial privacy and regulatory oversight. Traditional financial systems allow some level of privacy for individuals but give authorities the ability to trace transactions when investigating crimes. Ring signatures make such tracing extremely difficult or impossible, which raises concerns about money laundering, tax evasion, and funding of illegal activities. Different jurisdictions have taken different approaches to this tension. Some countries have banned or restricted privacy-focused cryptocurrencies that use ring signatures. South Korea, Japan, and Australia have pressured exchanges to delist privacy coins. The reasoning is that the inability to trace transactions makes these cryptocurrencies too risky from an anti-money laundering perspective. However, these bans are difficult to enforce because cryptocurrency is borderless and peer-to-peer exchanges are hard to regulate. Other approaches include optional transparency features. Some privacy coins allow users to voluntarily reveal their transaction history to specific parties, such as auditors or tax authorities. This is done using view keys that allow decrypting transaction amounts and proving which outputs belong to you, without breaking the ring signature anonymity for others. This gives users privacy by default while allowing compliance when necessary. There is also research into selective disclosure systems where users can prove properties about their transactions without fully revealing them. For example, you might prove that your total income exceeds a certain threshold for tax purposes, or that none of your funds came from a sanctioned address, without revealing your actual transaction graph. These systems use zero-knowledge proofs combined with ring signatures to enable compliance without sacrificing privacy. The debate continues about whether financial privacy is a fundamental right or a threat to law enforcement. Proponents argue that privacy is necessary for freedom and that legitimate users shouldn't have their financial lives exposed. Critics argue that the inability to trace criminal funds is too high a price for privacy. Finding the right balance is one of the major policy challenges as cryptographic privacy technology becomes more widespread. Practical attack scenarios. While ring signatures are cryptographically secure, real-world implementations and usage patterns can create vulnerabilities. Let's examine practical attack scenarios that have been discovered or proposed against ring signature systems. The temporal analysis attack exploits the fact that most users spend outputs relatively soon after receiving them. If an attacker observes when outputs are created and when they appear in ring signatures, they might guess that the newest output in each ring is the real one being spent. Early versions of Monero were vulnerable to this attack because users could choose their own ring members, often selecting old outputs as decoys. The fix was to use a selection algorithm that mimics real spending patterns, making the real input indistinguishable from decoys based on age. The chain reaction attack occurs when an attacker controls multiple outputs that appear together in rings. If the attacker can prove they did not spend their own outputs, they can eliminate themselves from the anonymity set. If many rings overlap with attacker-controlled outputs, the attacker can, through elimination, narrow down which outputs were actually spent. The defense involves ensuring that rings are selected with sufficient randomness so that overlap is unlikely. Additionally, using large enough rings ensures that even with some elimination, anonymity remains strong. The poisoned output attack involves an attacker creating many outputs with known properties, waiting for them to be included in other users' rings, then using knowledge of these outputs to reduce anonymity. For example, if an attacker creates outputs with specific amounts and knows those amounts weren't spent, they can eliminate those ring members. The mitigation is ring CT, which hides amounts, making it impossible for attackers to create distinguishable outputs. Network analysis attacks do not break the ring signature cryptography but instead analyze network traffic patterns. If an attacker can observe when nodes relay transactions, they might correlate transaction announcements with IP addresses to guess who created which transactions. Even with ring signatures hiding the sender in the transaction, network-level linkage can reduce anonymity. Solutions include using Tor or I2P for transaction broadcast, and implementing Dandelion++, which obscures the transaction source by having nodes relay transactions along random paths before broadcasting. The most dangerous attacks combine multiple techniques. An attacker might use network analysis to narrow down possible senders, temporal analysis to further reduce candidates, and control of some ring members to eliminate more possibilities. Defense in depth is crucial. Use large rings, algorithmic decoy selection, amount hiding, network anonymity, and regularly update the protocol to address newly discovered weaknesses. Future developments and research. Ring signature technology continues to evolve, with several exciting research directions promising to improve privacy, efficiency, and functionality. Let's explore what the future might hold for ring signatures and anonymous verification systems. Post-quantum ring signatures are becoming increasingly important as quantum computers advance. Current ring signatures based on elliptic curves will be completely broken by quantum computers running Shor's algorithm. Researchers are developing ring signature schemes based on quantum-resistant foundations like lattices, hash functions, and isogenies. Lattice-based ring signatures are particularly promising, with schemes like Raptor achieving reasonable signature sizes and verification times while resisting quantum attacks. The challenge is that post-quantum signatures are generally larger and slower than elliptic curve signatures. Logarithmic size ring signatures represent a major efficiency breakthrough. Instead of signatures growing linearly with ring size, schemes like Triptych, Arcturus, and Lelantus make signatures grow logarithmically. Future work aims to make these schemes even more efficient and to reduce their trust assumptions. Some researchers are working on fully transparent schemes that require no trusted setup at all. Recursive ring signatures would allow building ring signatures on top of ring signatures, creating anonymity sets spanning multiple transactions or even multiple blockchains. This could enable privacy-preserving smart contracts where contract execution is anonymous, or cross-chain protocols where the source chain, destination chain, and user are all hidden. Accountability mechanisms that preserve privacy except when necessary are another research direction. The idea is to build systems where normal users have full anonymity, but if specific accountability conditions are met, certain trusted parties can decrypt or trace transactions. This might involve threshold decryption where multiple authorities must cooperate to break anonymity, or time-locked encryption where anonymity expires after some period. These systems try to satisfy both privacy advocates and regulators, though both groups are skeptical. Integration with other privacy technologies is an important frontier. Combining ring signatures with mixing protocols, zero-knowledge virtual machines, fully homomorphic encryption, or secure multi-party computation could create much more powerful privacy systems. Imagine a blockchain where not only senders are anonymous but also the computation itself is hidden, or a voting system where voter identity, vote contents, and tally computation are all verified without revealing any private information. These ambitious goals require breakthroughs in multiple areas of cryptography. Here text as per instructions. Implementation best practices. Implementing ring signature verification correctly and securely requires careful attention to many details. Let's discuss best practices that developers should follow when implementing or using ring signature systems. Use well-tested cryptographic libraries rather than implementing primitives yourself. Elliptic curve arithmetic is extremely subtle, with many opportunities for implementation bugs that create security vulnerabilities. Libraries like libsodium, OpenSSL, or specialized curve implementations like ED25519 have been extensively tested and audited. Even with good libraries, you must use them correctly. For example, always check return values and ensure constant time operations where necessary. Validate all inputs rigorously before processing. Every public key in a ring must be checked to ensure it's a valid point on the curve and not the identity element. All scalar values must be checked to be in the correct range. The signature format must be canonical to prevent malleability. Skipping input validation has led to vulnerabilities in real systems where attackers crafted invalid signatures that bypassed checks or caused crashes. Implement proper error handling and never reveal information through error messages or timing. If verification fails, don't indicate which part of the signature was invalid. This could leak information about which ring member the verifier suspects is the real signer. Use constant time comparisons for all cryptographic checks to prevent timing attacks. Be careful about cache timing, branch prediction, and other microarchitectural side channels. Test extensively with both valid and invalid signatures. Generate signatures with correct and incorrect keys, malformed curve points, out-of-range scalars, and edge cases like zero values or maximum values. Use property-based testing to automatically generate test cases covering the entire input space. Fuzz testing can find corner cases that manual testing misses. Include tests for side channel resistance if constant time operation is required. Document your implementation thoroughly, including security assumptions, trust model, and known limitations. Specify exactly which ring signature variant you are implementing. There are many subtly different constructions in the literature. Document the serialization format precisely so other implementations can interoperate. Provide clear guidance on secure parameter selection, such as ring size, curve choice, and hash function selection. Make it easy for security auditors to verify that your implementation matches the specification and follows best practices. Conclusion and future outlook. Ring signatures are a powerful cryptographic tool for protecting privacy while maintaining verifiability. As we have explored throughout this presentation, they achieve the seemingly impossible goal of proving authorization without revealing identity. This provides a foundation for anonymous transactions, whistleblowing, and privacy-preserving systems. The verification process for ring signatures is mathematically elegant yet practically complex. It requires checking that a ring equation holds across all members while treating each position symmetrically to preserve anonymity. Modern implementations must balance cryptographic security with computational efficiency, using techniques like batch verification and parallel processing to handle the demands of real-world systems like Monero. The anonymity guarantees of ring signatures are strong but not absolute. They provide information-theoretic anonymity within the ring, meaning computational power alone cannot break the signer ambiguity. However, metadata analysis, network observation, and behavioral patterns can reduce privacy in practice. Maintaining anonymity requires careful attention to implementation details, ring selection algorithms, and integration with other privacy technologies like Tor and confidential transactions. Looking forward, ring signatures will continue to evolve. Post-quantum variants will become necessary as quantum computers advance. More efficient constructions will enable larger anonymity sets without proportional increases in signature size. Integration with zero-knowledge proofs, smart contracts, and cross-chain protocols will unlock new applications. Regulatory frameworks will adapt to balance privacy rights with legitimate oversight needs. The fundamental insight of ring signatures, that we can prove group membership without identifying the specific member, has applications far beyond cryptocurrencies. Any system requiring anonymous authorization can benefit from this technology. As privacy becomes increasingly important in our digital world, ring signatures and related cryptographic techniques will play a crucial role in protecting individuals while maintaining system integrity and accountability. Thank you for your attendance. Please consider subscribing to the channel.